So here we go. Lesson 2, again, should all be review. So let's jump right into it. One-dimensional force problems. We're going to look at things, the elevator or apparent weight problems, air resistance problems, friction problems, and what's called the mini body problem. Here we go. The normal force is, to review, a contact force between the floor and an object. It is the force with which the floor pushes back up on you. Interestingly enough, the normal force is also the value that a scale would read if you were standing on it. The scale do not read weight. What scales are actually measuring is your normal force, which is an interesting thought. Some notes I want to make here. Contact forces between the floor and the object. Doesn't have to be a floor. It could be any surface. It could be a table, for example. And these scales, as we've said already, are reading Fn. That is how hard the scale pushes back on you. So example 1, if the person with a mass m and weight w is in an elevator standing on the bathroom scale, a real physics scale that reads in newtons of force, not mass in kilograms. If the elevator starts at rest and accelerates up, what's the scale going to read? So if this is the scenario, I'm going to draw it out here for you. You've got an elevator car. You've got a scale on the ground. And you've got a person standing on the scale. Okay? The elevator has a cable attached to it. Label some forces. We have force of tension acting up on the elevator. We've got a normal force acting up on the person. And we've got Fg acting down on the person. We've got Fg acting down on the elevator. Okay, so those are all the forces acting on this scenario. The question is, if the elevator starts at rest and starts to accelerate upwards, so we have an upwards acceleration, what is the scale going to read? Is the scale going to read a value that is the same as the weight, greater than the weight, or less than the weight? Now, we've already said scales measure normal force. Okay, so they're measuring the force pushing upwards on the person. In this case, because the elevator is accelerating upwards, the person is accelerating upwards. It means Fn has to be bigger than Fg. So those are the only two forces acting on the person. If Fn is bigger than Fg, Fn is going to be larger than W, which is equal to Fg. At rest, scale would equal the weight because the scale is measuring Fn. That's equal to Fg. At rest, Fn equals Fg. Okay. If our person moves upwards, Fn has to increase. Okay? It's as simple as that. Because the only two forces acting on the person are Fn and Fg. If the person's moving up, Fn's got to be bigger. Or sorry, if the person's accelerating up, Fn must be bigger than Fg. That's it. Okay, flip the page. Skip example 2. Let's keep going. So here's the question. A 35 kilogram student stands on a kilogram scale, which reads normal force divided by 9.8. If the elevator accelerates downwards at 2.25 meters per second squared, we want to find the normal force and the scale reading. So let's draw the forces acting on our student. We have Fg downwards. And we've got an Fn upwards. We know that the acceleration is downwards. And it doesn't really matter which way we call positive. So in this particular question, I'm going to say that down is going to be our positive direction because that's the direction of the acceleration. So we can put a few more things in here. We know that Fg is equal to her mass, 35 times 9.8. So that's going to equal 35 times 9.8, 343. So we can start attempting this problem. Dynamics problem. So after you draw the free body diagram, you're always going to start with F net equals ma. And let's start filling it in. F net, the sum of the forces. We said downwards was positive, so this is going to be Fg minus Fn equals the mass times the acceleration. So 343 minus Fn is going to equal the mass, which is 35 times 2.5. So 343 minus 35 times 2.5 is going to equal Fn. I just added that over. I subtracted this over. And we're going to find that Fn equals 264.25 newtons. So the acceleration is downward, so we expect Fg to be larger than Fn, and it is. So there's A, the scale reading part B. The scale is equal to Fn over 9.8. So that's going to be 264.25 over 9.8. That's going to equal 264.25 divided by 9.8. 26.96. This is that's what a typical bathroom scale would read, which is why we would say, oh, that's my weight, but no, it's actually measurement of mass. So it's like you have less mass, but you don't. You just have smaller Fn, and the Fn converts it to what your mass would be for you to feel this way. Okay, so there's a fundamental difference there. Flip the page. We're not going to do all of this. Let's talk through example 4 here. We're going to draw some force diagrams of this situation. Okay. So air resistance is the force of air molecules bumping into an object that is moving through the air. It's like friction. The force of the air resistance has a direction opposite to the motion. So you've got an object that has ridges and bumps and grooves and stuff on it, and the air molecules catch in these things and push back against our ball. Now, air molecules don't weigh a lot. They're pretty small, but there's lots of them, and so they impede motion. Have you ever been on a ferry, like running into the wind? You'll have felt this. The impact of a lot of air molecules moving quickly is going to slow you down. So what's happening here? The ball is being thrown, so that tells us there's an applied force upwards. There has to be. There has to be Fg downwards. And if the hand is moving up, there's also going to be F air down as well. There's going to be F air down here and Fg down here. And we're still going to have Fg down here, but in this case, because the object is falling down, we're going to have F air going backwards. Okay, the air resistance always opposes motion, just like friction does. Okay, flip the page. We've got this scenario here. A 90-kilogram parachutist free falls for a time and opens a parachute. If the parachutist slows down at a rate of 1.5 meters per second squared, we want to compare the forces that act on the system, write the force equation, and then find the force of air resistance on the parachute system. Okay. Here we go. First, this is the scenario. We have a person falling through the air. Okay? You've got gravity acting downwards on this person. And we have air resistance, or the force of the air back upwards. For a while, Fg is going to be bigger than F air. And that while is going to be from the time she steps out of the plane until terminal velocity is reached. And at that point, terminal velocity is the maximum speed for a free-falling object. It's different for all sorts of objects because terminal velocity occurs when Fg equals F air. And you can change this. Like you've seen this in TV shows and movies and stuff. When a person has reached terminal velocity, they're falling, but when they're falling like this, terminal velocity is slower than if this person were to suddenly dive. You could fall faster than someone falling like this. You've seen this in action movies all the time. And that's because F air is dependent on a lot of things. It's dependent on your orientation. It depends on how streamlined you are, that kind of thing. The terminal velocity is when Fg equals F air, and you are no longer accelerating at this point. Then a person opens the parachute. She pulls the cord, parachute opens. She got shorter somehow. And at this point, you've got Fg acting downwards, but you've got a really big F air acting upwards. We know that the acceleration, so the person is slowing down at a rate of 1.5 meters per second squared. So the acceleration, that means the acceleration is backwards. Or sorry, I shouldn't say backwards, upwards. Okay, they were falling, some terminal velocity, pull the cord, now she slows down because F air is acting. So we're going to call up positive. Here we know that F air has to be bigger than Fg because she's slowing down. So when we've got F net equals ma, I called up positive, so this is going to be F air minus Fg equals ma. F air is what we're looking for. She's 90 kilograms, so I know the value for Fg. Whatever, I'll just put it into the equation down here. Minus 90 times 9.8 equals 90 times 1.5. If you run that, you're going to find that the force due to the air is 1,017 newtons. Flip the page. The force of air resistance is actually not a constant value. In fact, the force gets larger as speed increases, which kind of talked about already. A falling object will eventually reach the point where the force of air resistance equals the weight of the object. I talked about this already. This is terminal velocity. We don't necessarily. I'm not going to graph this. We're going to skip example 8, and I'm just going to get you guys straight into the homework. So I want you to try the following. I want you to do 1, 2, 4, 5, and then I want you to do 7 to 9. There's a lot there. This, again, should all be review. There's going to be more review. Next lesson, we're talking about friction. The lesson after that, we're going to talk about, we're going to do like the many body problems, so bolt-on blocks over pulleys and stuff like that. All of that should be review. And then we're going to start to get into, oh yeah, we got more pulleys. All of this is a review leading us into, yeah, we're going to do some vector stuff kind of up here. And we need this for the torque stuff. So yeah, a lot of review here. Should be relatively easy. Got any questions, let me know. No judgment if you're struggling. Feel free to ask. Good luck.